we were going to start today on chapter 11, which is about taking the off policy case now that we're in the section on approximation. And the idea behind the off policy methods is that, we use there's some behavior policy which we're able to use to interact with the environment. The goal is usually to find either, the correct values of some target policy or to find the optimal policy. And in the past, we had motivated off policy methods by perhaps there's a situation where you can only collect data from an environment, with a fixed policy, but you still want to be able to find the optimal policy. And the technique we had used, which I'm not going to go all the way back to it, but it was in chapter 5. And in chapter 5, in the tabular case, we had used this importance sampling ratio. And the idea behind importance sampling is you're computing the relative probability of all of the action selections between the target policy and the behavior policy. So this, and then if you want to approximate the values, but you only have samples from the behavior policy, then you have to adjust the samples with this ratio. And there was we had weighted importance sampling and regular importance sampling, and methods of updating each target. But you just have to keep track of this ratio, which means you have to keep track of which actions were selected, and you also have to know what the probability distribution is of the policy that you care about here. Now, there was, another off-policy method that was considered earlier was, here, if I can sit in here, was, Q-learning, which is probably the most well-known off-policy method. And in Q-learning, we're learning here action values. And we have this update where, notice how this update rule for Q-learning doesn't reference any policy. So during Q-learning, when there's this loop here where we go through and we collect samples from the environment. And there's some policy being followed to collect these samples. Here, there's no, the arguments to this function don't contain a policy, because what you do practically are here. I mean, there's some policy initialization here, but basically this policy will start out as some random policy. And then throughout the process, you update it, typically, you don't have to do this, but to be efficient, you would make this the epsilon greedy policy with respect to the current value function. And the reason why you make it epsilon greedy is so that you still guarantee this exploration of the environment. Whereas normally, if we were to just treat this where we're only taking greedy actions, that would not be guaranteed to converge, because we could get stuck by revisiting the same states over and over and never, updating all the values. So we had done this, and because, in Q-learning, the update rule, this is sort of an expected update where we're using the Bellman optimality equation. So instead of actually computing these probabilities over the transition state, we're just taking the maximum, because for the optimal policy, we know that, this update should result in no change to the policy when it's converged. So because of this, there was this advantage to Q-learning where you didn't have to worry about the importance sampling ratio, because, we're learning action values and, we're considering all the transitions, and whatever policy we're using to explore here is going to eventually visit all the states, and then all of these state action values will eventually get updated to the correct value and converge to the optimal value. So that was all fine in the tabular case. But now, in the case of approximation methods, there is an additional problem with that. which is that, you know, we're not going to be able to calculate, to have all these values converge. Like there's going to be some parameter space. This is an approximation. And that's why, for this type of learning, for off-policy methods, we had introduced, I guess, in chapter 9, this, value error objective, where in the value error, what we're trying, and this, by the way, like this value error had nothing to do with finding the optimal policy. This is just to try to collect the correct, values. So you could use this to try to get the best parameters for the action values and then do, the same sort of like policy iteration that we did before, but we had already discussed how we also don't have the policy improvement theorem anymore, but like that's still an attempt that's made in the case of approximation. But in order to even, have the values to begin with that we then work with, if they're action values, we have to first, optimize the values or optimize the parameters with this objective. And this objective, what we're going to have to, have some way to estimate this, like the true values. So we can either use like the Monte Carlo returns, which would be, an estimate of this, or the bootstrap methods, like we discussed with the TD methods. And then, this is the current approximation value of that state. But then for this to work, however we're updating this, like we had derived these gradient methods to do it. And we can do these gradient updates, but this gradient update will only minimize this if we, sample states according to this distribution. And right, this mu, this was the steady state distribution of whatever the policy is. And, in the past, we could just sort of update all the states, and we just wanted to update all of them an infinite number of times and in the limit, and that was good enough. But now, we have this other factor which didn't happen in the tabular case. So what's mentioned in the first part of this chapter is how like we can use the importance sampling ratio. Like the importance sampling ratio operated on this part of the equation where like the samples we're collecting to estimate this, have to be corrected because we're not actually, sampling V pi, we're sampling something else. Like, so here we're going back to discussing the importance sampling ratio here. And in this chapter, it's only going to be looking at these bootstrap methods. The reason for that is probably because, they're generally more desirable if you can do it, because if you have a continuing problem, like one that doesn't have terminal states, then you can't even use, like you can't just sample this with Monte Carlo sampling because the episode will never terminate. So then we're sort of stuck doing a bootstrap estimate. And that's what's shown here is like, this is an example of one of the bootstrap estimates, which is just, like the TD0 estimate, where we have the reward. And then here we're, estimating the value at the next state with the approximation function. So, and this already had problems before, right? Because then we don't have these like true, this gradient update is no longer like actually the correct gradient update because, the parameters actually affect this target value in here. So, that was already one problem. But now, imagine like this whole step that we're taking is from a different policy. So, then that's what the importance sampling ratio is doing here, is it's correcting whatever this sample is, so that in the long run, as we average this together and we see different samples, these updates are going to, in the long-term average, equal the updates we would get if we were following the correct distribution here. Right, so just like before or in chapter 5, the whole thing that we're trying to correct here is that, these deltas and these samples are no longer going to represent the target policy. So then, this ratio ends up correcting that. But, the other problem, which isn't addressed by doing this, like if we just do updates like this and we're following the behavior policy, you notice that like the states we visit now are no longer going to follow this. And actually, yeah, this should be, oh, sorry. Sometimes this is written with a little I under it. Here it's omitted, but this distribution is for a particular policy, in this case, like pi. So we'll see, or there's a bunch of examples here in this chapter where you try to do updates like this, and even if you use the importance sampling ratio, it still might not work, or it might not be a stable process because the samples themselves are not correct or not following this. So then this whole, like everything we used to derive what these gradient updates should be is no longer valid, right? Because we had always assumed that this was the case. And then what we end up optimizing here is just a completely different objective, because right, it's going to be some objective where we're weighting the error in each state according to a different distribution. So are there any questions about that, or how, like the fact that there's two different, like unlike in the tabular case, in the approximation case, there's actually two different things we may have to correct to get the right updates. Okay, well, if that's clear, yeah, we can move on. So, so far, all of the update rules being presented are just look exactly the same as what we saw in the previous chapter, except, we have this importance sampling ratio now modifying these deltas, right? And like these deltas represent whatever the target value is that we care about, minus the current approximation. So like here, this is for expected SARSA, where now we're using the distribution of the policy. And again, just like in Q-learning, we have for expected SARSA, which like for Q-learning, instead of this sum over A, you have the max of this over A. I mean, in Q-learning, like the policy is actually being updated. But here with expected SARSA, we're just trying to estimate, the value of this policy. And here again, because we're actually considering all of the potential actions and the transition values, we don't have to worry about the importance sampling ratio, which seems kind of nice. So like this maybe should work and like have nice convergence properties. But again, the problem is that we aren't, oh, sorry, I should show this again, is that like we're not actually going to draw the samples from this distribution. And here, this is just additional update rules for the n-step methods, which I'm not really going to go into because, like the n-step methods are just like the one-step method, but extended over longer, you also have to multiply the importance sampling ratios together. Here, this is like just the product of them, because you end up taking different actions multiple times consecutively. So then this represents the probability, like the different, like the probability ratio of this trajectory happening for these n steps between the two policies. So yeah, and then there were some other methods considered, like, so these were all in chapter 7, but there was sort of mixed methods where you would do like expected updates in certain steps, and then the sample updates with an importance sampling ratio on other steps. And go back, I mean, it's not, these first two exercises here are just asking to convert whatever these n step methods were from chapter 7 and convert it to a semi-gradient method with approximation. So it's not, they're all kind of the same answer, or they all look very similar to what is done in the book here. But first, like, you have to define like this importance sampling ratio over a certain number of steps. And that, again, this is just the product of those ratios. And then, right, this was like the off policy n step update that we had from chapter 7. And then, in order to convert it into this semi-gradient method, it's all like, everything's very similar, where we just have this product of the importance sampling ratios here. And then, this G target, right? This is like the, do I have it? Yeah, so I have it defined down here, where whether you're in the discounted case, like here, this is for a discounted return, and here, this is for the average reward estimate, but where we add up the rewards up to, the n steps. And then on the final step, we use whatever the current, approximation value is. So in the tabular case, this was just, whatever the current state value estimate is here. And here, this is v hat, where we're using, whatever the weight vector is at this previous step. So yeah, I think this is correct, but honestly, these n step methods, we're gonna end up replacing them in the next chapter with these lambda methods. So I wouldn't worry too much about this. This Q sigma method also, yeah, I mean, it's probably not worth going into this, because this was one of the more like obscure methods they had, which involves, this was, I think, the tree, I don't know, that there was some kind of tree method here where we had combined different estimates together. But yeah, you can look at the solutions later, but it ends up following the same pattern as what it shows in the book, where you just sort of, you have this gradient of the estimate, and then, you replace whatever the tabular estimate was with the parameter estimate here. Yeah, so for simplicity, I would just think more about like this delta, like the one step off policy method. And the nice thing about the one step method is also like the expected update doesn't even, reference the importance sampling ratio. So that's nice. And yeah, and then in that case, we don't have to worry about any instability with that ratio. The only problem is the difference in the distribution of the states that are visited. Okay, so now, like, yeah, now that we've introduced the methods, the bulk of this chapter goes into these pathological cases where we get, like some major problem with the semi-gradient method. And, the source of the problem is really the fact that when we do approximation, like state values are connected to each other. So just as a conceptual starting point, there's this idea that you imagine, a particular problem where there are two states that are connected to each other like this, where like one state always transitions into another state. And then because of however, whatever form of the function approximation is, these values are forced to be connected in this way, where one is estimated with a value of W and the other is estimated with a value of 2W. And then, the rewards are 0, in this case on all transitions, yes. So there's always a reward of 0. And then the idea is like, so consider what this, the TD update is from the transition that goes from this state into this state. Right. So when we do the TD update, we take, this is the TD estimate, which is the reward plus the discount rate times the value here. And then we compare that to the current estimate. And in this problem, the reward is 0. We don't have to worry about that. And then the estimate of this second state is 2 gamma. And the estimate of the first state is 2W. And the estimate of the first state is W. So we have, a delta that looks like this. Right? And then if we then take this and apply the weight update, or the semi-gradient weight update, the importance sampling ratio, again, like there's no, like in this case, oh, sorry, I'm gonna mute you unless you have a question. There's some background noise. Yeah, so again, like this gradient term is going to be just 1, right? Because like the estimate here is just W. And then the importance sampling ratio is 1 because there's not even multiple actions here to consider. So then, we get this form of the update, and we have this update that looks like we're going to take, whatever the original parameter was and multiply it by some number, right? And the number here is 1 plus alpha times 2 gamma minus 1. And wait, I'm trying to see if I plotted this out. Okay, yeah, so if in this case, we know gamma is between 0 and 1, and we have this 2 minus 1 here. So it's clear here that if gamma is greater than 0.5, right, then this whole expression is greater than 1. Right? So if we keep doing these updates, we have, 1, so like some number greater than 1. And, this is going to be to the, like some power, like the nth power, where n is the number of updates we've done. And if this whole constant is greater than 1, then this whole process diverges. And if it's less than 1, then it correctly converges to 0. Now, this isn't like a full problem here because in general, like unless this is a terminal state, we would have, eventually transitions out of this state. And then like all the transitions out of this state would possibly, then correct this value back to the correct value. But as a thought experiment, they consider if we do this in an off policy fashion, then consider that every transition we take out of this state, let's say like under the behavior policy, never occurs under the target policy. So, if we look back to the importance sampling ratio, let's say that when we exit, this pi of whatever that action is 0 under the target policy. So then this is 0. And then whenever this is 0, we just don't do the weight update. We just conceptually, it's saying that if the behavior policy ever takes a step that would never occur under the target policy, then don't use that information to do the weight update. So that can definitely happen under off-policy training. And then if that is the case, like there's no way to guarantee that's not the case. Like you could very easily select a behavior policy that did that. Then, this weight update, this is the only time it would occur. And then this value would just blow up to infinity. So clearly, like this is a case of some sort of instability. And like the source of the instability is the fact that these two values are linked. And because of the off-policy training, we only end up doing updates that cause this to diverge. It's not a problem if gamma is less than 0.5, but we're free to select whatever the discount rate is. Clearly, in this situation, the correct state value should be, well, we don't actually know what the correct state value is because it depends on what happens after here. But the values diverging is never correct for any value of gamma less than 1. But this is sort of like a little introduction to the actual examples where we have this off-policy divergence. But are there any questions about this? Just like the concept here of like if you see a weight update of this form with this multiplicative factor, then it's going to diverge if this factor is greater than 1.
I washed my hands and my face.
Oh. Okay, sorry. Are there any actual or questions about this? Yeah, this like introductory toy example.
No, that's great.
Okay, so here we'll get into the first like real example of this, which is from, yeah, maybe somebody. This is actually from it's some like a lot of the examples in this chapter are from certain like papers that were written by either like Baird or later on this other example here, these two guys. And their papers go into a lot more, details about the math behind it. I mean, but I'll try to go into some more detail here too. But in this counterexample, this is set up as a continuing problem, and forget like at first you can forget about these parameters in here, but imagine like there's just 7 states in this problem, right? So there's 7 distinct states. All of the states up here, and actually, how do I do this? Hold on, I'm trying to remember of how yeah. So so we consider 2 policies, and this problem has 2 actions in it. So there's the dashed action and there's the solid action. Now, the dashed action will produce a transition where there's an equal probability of being in any one of these 6 states at the top. And then the solid action, if you're in one of these 6 top states, it will take you into this 7th state. And if you're already in the 7th state, it will keep you in the 7th state. Right? So if you follow the policy that only takes the solid action, which is in this case the target policy, then the problem will just stay in this state indefinitely. Right? If it starts up here, it'll transition into here and then just stay here. Whereas the behavior policy is constructed in such a way where we have this 1/7 chance of taking the solid action and then a 6 out of 7 chance taking the dashed action. The reason for this ratio is just to create a situation where I'm showing here, if you actually like sample this, I think this, I mean, you can calculate this analytically, but this is showing if you follow this policy in the problem, this is the state distribution that you end up getting, right? So this is a distribution where there's just an equal probability of being in any of the 7 states. Okay, so, and again, like this, if we think back to the tabular problems, or if we do like dynamic programming to estimate these values, we would like sweep through the state space, and we would maybe do an update like for every state, which would mimic this behavior policy. So like this behavior policy is going to sort of, mimic the extreme case of just visiting all the states an equal number of times. Whereas, the target policy has a completely different distribution of values. So, fine, like this is a problem we could solve perfectly fine with, tabular methods. But here, we're considering this approximation where we're forcing this relationship between the values. Now, this is also a case where, even though we're doing function approximation, like we saw in this example, right, whatever W is, the only options we have to value these two states are, W and 2W. So these are not independent values. Now, in this example, the state values are linked somehow, but notice that there's 8 of these parameters here. So this is actually like over parameterized. So even though the values are linked, there is actually an infinite number of solutions that produce the correct values here. One solution is for all the W's to be 0. Again, in this problem, all the transitions have a 0 reward. So it's just a completely, trivial problem. Like all the state values are 0 for any gamma less than 1. But, if we look at like these, all these values of W, like as long as W7 plus 2W8, is 0, we can set this for all these, then this is going to produce, something with absolutely 0 value error, right? And that's going to be true of both policies, right? Because it actually doesn't matter what the policy is. The values are 0 regardless of the policy. So, fine, we have a problem where the approximation itself is not, limiting the ability of the function to be correct, right? But the gradient, that doesn't, just because there is a solution like that, it doesn't mean that the gradient updates that we take are actually going to converge. And that is the point of this example, is that we're going to see that if we actually try to do gradient updates with the behavior policy, we end up with diverging values. And again, like it's not because the function isn't able to approximate the values. It's more because of like the actual distribution of visits. It also depends on the initialization. So we'll see here. If you actually, start out with all the weights being correct or being 0, then then they'll stay 0. But the problem is if you start out with any other initialization, the weights end up diverging. So if you want to see, so we can end up like, actually in this example, so I believe in the paper, it would actually derive this analytically. I'm not sure if this divergence can be derived analytically, but empirically, this is what happens. This is what happens when they use this particular weight initialization on this, right? So there's 8 values here. And I think in my code, I made some of these plot. So yeah, I don't remember now if I think I did use the same, yeah, like weight initialization here of using this. But so this is showing, like the semi-gradient dynamic programming update. Now, here, when they say dynamic programming here, when they do it in the book, well, first of all, you end up doing this like actually calculating this expected value here, because we actually know what the policy distribution is here, and we know all these other things. So that's fine. But notice here, so they're saying like this is the weight update they do for dynamic programming. And this involves a sum over all the states. And it's convenient. Like if you look at the behavior policy, it does this. So they're saying like this dynamic programming update is equivalent to this off policy method where you're following this behavior policy. Because this inherently, the way this sum works, is it's weighting all of the states equally, right? And if we were to do this off policy TD, we wouldn't sum over the states equally, but rather follow the behavior policy and collect samples that will happen to also, end up sampling all of these an equal number of times. So that's why these should, this is basically just showing, a smoothed out version of this, because these are the exact, this one has sampling error for the weight updates, and this one doesn't. But I did want to show here. So, if you think about like doing dynamic programming and what we had done in other chapters, here, like this function will do dynamic programming with, some sort of function approximation where we have some policy function that we're trying to approximate, right? So here, this is just some function that we can use to update the probabilities of all of the action probabilities. So remember, for this example, the behavior policy is just one action has 100% probability, or sorry, the target policy, one action has 100% probability and the other action is 0, right? And this is the distribution in the behavior policy. So there's this update step, I'm sorry, and it's sort of hidden inside of here, but there's this part where like this whole thing is occurring inside of this function, where this piece is computing the action values, where, yeah, like this expected value of pi inside of this, we can compute this by summing over the actions and using the probability of each action. And then we have to compute the gradient. But the difference here is that, like, this problem could be a tabular problem, but we would always use approximation in a problem where we don't, it's not feasible to go through all the states. So, actually doing this sum is not really possible. So if you want to write a function that does this, semi-gradient dynamic programming for a non-tabular problem, you do have to, sample the environment, or like you have to sample states at least. So here, right, I'm going through some number of steps or episodes, and at this point, I'm going to use the actual environment to take an action. Like I'm going to sample an action from the distribution, and then I'm going to, sample the reward and the next state from the environment. And then, this update, like all this stuff in here is going to occur, but instead of taking this sum over states, what I'm doing is, doing this update for whatever state I'm in, and the states I'm in are going to get updated by this. So in this version of the dynamic programming function, this is not really an off policy method. And notice, like, I don't actually have a behavior policy here. And the reason is because the reason why this diverges is because, if you actually want to do dynamic programming like this, you can't have a behavior policy, or like you shouldn't, because then you're going to be screwing up the states that show up here on these transitions. And in this case, if I were to use the behavior policy in the chapter, it would be equivalent to this, right? Where I would just be, on average, summing all of the states equally. But doing it this way, and this is like what was referred to earlier as a trajectory sampling, where like I'm still doing the dynamic programming update, but I'm using some trajectory using this on policy distribution. And then, yeah, this is like doing the linear version of it, but I'll show it here. So what this graph is showing is how the weights change when you do this dynamic programming with either the behavior policy or the target policy. So here, like with the behavior policy, right, all the states are visited an equal number of times. And then this is how the weights change over time. This is showing like all 8 of the weights. And you'll see like that the weights themselves are not going to 0. It's finding a different solution. But the solution it's found, this is just an example of 2 of the state values. So like state 1 here and state 7. And you can see that, both values are correctly converging to 0, right? Which, like, all the values here should be 0. And then if I instead, oh yeah, so this, if I set the initial value to, this was like shown in the book, but if you set the initial value to 0, then everything is just going to be 0 the whole time because it's already at the correct answer. And then if you set the value to something other than 0, it will find, some other combination of weights. But you can see in all these cases, right, the actual value estimates are still going to 0, right? Here, like regardless of what this initial value is. Now, if I do the same thing for this policy, remember in this policy, we start out in some state and then we just end up here and stay here forever. So you can see that now one of these values, like the value hasn't converged. Now this value has correctly converged to 0. This is for state 7. This is the state that it's spending all the time in. The reason why these other values don't converge is because, the way I'm sampling this, it never spends any time there. And you can see, right, if you look at what I showed before, which is, the target policy distribution, if this is a continuing problem, then 100% of the time is going to be spent in this state. And if you look back to what this prediction objective, if there are states where the probability of being in the state is 0, right, their values don't matter at all for the approximation. So the reason why in this case, like this value is not converging is because like this value doesn't matter at all regarding the this policy. But this isn't a case of divergence, right? Like this isn't diverging at all. It's just the value is just not being updated because we never end up leaving this state. So in this case, if you do dynamic programming, sampling the states correctly according to the on policy distribution instead of just weighting them all equally, then these values converge just fine. And they converge to the exact values because, right? In this, we have enough parameters to actually compute the values exactly here. And they should all be 0. But I say, J, your question is the initial values are just, typically we just randomly initialize them because you have no, I mean, like there's no prior belief here to begin with because you don't even know what these parameters represent in a generic problem. You know, that's what like the gradient update process, like this form of the function here is just arbitrary. It's based on like, you know, the feature vectors that we've selected for these states. And like the feature vectors are just something that was selected. So yeah, like typically you would initialize all the values at 0, actually, maybe. That's a bad idea if you're doing like nonlinear approximation, because sometimes it won't move at all from 0. But
Yeah.
with a linear, you know, if we're doing like linear approximation, there's no problem with initializing it at 0.
Okay.
Yeah. In this case, also initializing it at 0 would never diverge, but that's also just a coincidence because, you know, the actual correct value happens to be 0. Yeah. So again, I think this is sort of like constructed intentionally here where the dynamic programming update they're doing just happens to match this behavior policy. But if this behavior policy was any different from this, then this distribution, right, wouldn't be equal. It would be something else. Like there's an infinite number of distributions we could have here. And right, they're all going to produce like, I mean, whatever it is, we should sample according to that in general. So I would say like it's not shown in the book, but like if you want to do dynamic programming for these approximation cases, I mean, another good reason not to do this is like you actually can't do this in general because right, the whole point is we don't have the ability to sum over states. And actually, you could also say like, well, okay, I will just use the random policy. Like instead of like here, like instead of taking steps using the true policy, I'll just use the random policy. But again, like even the random policy is not going to produce a distribution of states like this. Like if you look at this example, right, this policy that visits all the states equally is this policy. It's not the random policy. If you did, you know, 1/2 and 1/2, then this distribution would not be equal, right? You would end up on average spending way more time in this state, right? Because there's like 7 of these states that end up transitioning here. So, you know, this is, you know, specifically contrived to have this thing make sense. But yeah, so I believe like the real source of the divergence here is, you know, like you can see that you eliminate that problem completely if you just do this trajectory sampling, right? These are all converging to some value that they're not blowing up. But I will show here, so actually this is like older code that actually computes this example, and it's older because like this thing that diverges, I mean, the off policy thing is a little more straightforward because yeah, like the way you would do this in the way they're showing is you would just feed in, you know, a different behavior policy. And that's what's being done here is you're just like here, this is doing the full dynamic programming update. This is doing the expected, or I'm sorry, like this is like the expected value version of this. But in both of these cases, the trajectory being followed is from the behavior policy. And that's where you see these weights are all diverging, and the values are diverging. And then again, like this is showing, I already showed the DP update where the weights are not diverging. And then this is doing it with temporal difference learning where you're sampling. And then you see that there's no divergence in these cases. Is there anything more to this example? I don't think so. So yeah, we can move on to the next example. And I think if you look at the reference to this, whatever paper this comes from, there might be an analytical treatment of why this divergence happens. But I think, yeah, one of the main points here is that this divergence can occur even when you have an overdetermined system like this. And it's simply because we're not correcting for the states that we visit. And that you can imagine is like very hard to correct for, because like if you're following a completely different policy, you have to like look back. Like you would have to have like an importance sampling ratio looking all the way back through time, back to the start, and like to basically see, how often would this state be visited starting from wherever the starting point was. And that's not going to work either, because like imagine that you have actions, like in general, you have actions in the behavior policy that are never taken in the target policy. So here, like the dashed action is never taken in the target policy. So even if we wanted to use the importance sampling ratio to correct for the state probability, every time we encounter a zero here, the entire ratio becomes zero. And then we can't use the information at all. So you could imagine like you're going through an environment, like any sort of environment, and you end up following the behavior policy and you take an action like into a state that you would never be in under the target policy. And then after that, you continue to move. Like there's no way to take that trajectory and figure out, some corrected version of the states you'd be in under this policy. I mean, you would have to restart. I mean, yeah, like even if you restart the importance sampling ratio, you don't know the starting point of whatever the probability was of being in that state under the target policy. So that's why, like previously, like how do you sample the on policy distribution? Well, you sample it by following the policy. And if you can't follow the policy, then you end up with these situations where like you can't really do the correct updates. And they mentioned here in Q learning, this may not be a problem. And that's because when we do Q learning, the behavior policy is always very close to the target policy. And there's some, again, like there's no guarantee, but it's likely that if the two policies are close to each other, then these distributions won't be too different. And then you could hopefully avoid some of this diverging behavior. But then you have to figure out, well, exactly how close does it have to be? Would it start diverging, if the epsilon we use in Q learning is too large? So yeah, all of those concerns come up. But, this situation at least proves that, there's always some chance of this causing an instability here. Now, the next example, it can be treated analytically and shows more clearly under what conditions the instability happens. But, there's also a different reason why the next example has an instability. The thing that's so concerning about this example is that, like, it's not from the typical situation where approximation has problems, which is, this situation where we're not actually free to have the correct state values because, like, they're being connected in some way. They could be a problem, right? Even if we can fully, over-determine the system with parameters, we still have this problem of doing the gradient update with the wrong distribution of states. So yeah, are there any other questions about this example?
No, all good.
If not, okay. So here, try to look at the next example here. Okay. So this example also, right? This looks very similar to the situation we showed. In fact, it takes, right? It extends this example and just makes it a complete problem. So we have, two states plus a terminal state in this problem. And this is like also an episodic problem because of the presence of this terminal state. So this will always terminate in a finite number of steps. So if you start here, you transition into this state, and then there's a probability epsilon of transitioning to the terminal state, and a probability 1 minus epsilon of returning to this state. And then, so you can imagine this is state 1 and this is state 2, but we're imagining that we only have a single parameter to approximate these two state values. So the single parameter is W, and again, like this being W and this being 2W, that is arbitrary based on however we're representing the states. Like if these were feature vectors, basically, this would have a feature vector of 1, and this would have a feature vector of 2. And this could easily be a different constant, right? Like this could even be 1, in which case the two state values would be equal. Now, the reward is 0 on all transitions here. So for this problem, the correct values are just 0 and 0, right? And, that's perfectly possible to achieve with this parameter, right? Like W could just be 0, and then the problem would be done. But just because that, just like before, that doesn't mean that the actual gradient updates we do are going to produce that. Okay, so in this problem, I have it in a little more detail here, but we're going to imagine doing this update, and now this represents they're referencing the value error here, but notice like what this update is. This is like the TD0 target, right? And here we can actually use like the full expected value because we can compute this for this problem. And this is the current approximation value. So this is like imagining an update that we would do with like TD0 or like, expected TD0, like semi-gradient. And, instead of doing a gradient update, like, because this problem is simple enough, we can just write down like this quantity in the parentheses here with like it being squared. This is just like whatever that the value error is, but using this expected value. So this should be like the TD fixed point, or like this should be able to converge to the TD fixed point if we do this, right, because like, I think, actually it's possible this, I mean, this expected, yeah, like because we actually have this v hat in the expected value, I think this will, if we did this properly, it should converge to whatever the TD fix point is. But again, like in this problem, I don't know, that would require a little more. I'll have to see. I can try to add that before next time to my solution if seeing how this, what this converges to. But this is just saying, you know, if we take this TD like approximate, like TD0 estimate, and we sum it over the states, this is like the squared error of this, then we can just see like what is the W that minimizes this, or, you know, on this particular step. And we already know if we just set W to 0, like this error will be 0. But this is saying, well, let's see what this minimum is as a function of the current, you know, parameter value. Right. So if you look at how this is derived, what we end up with is, yeah, if WK is 0, then WK plus 1 will be 0. And that will be a solution. But what it's also saying is that if WK at any point is something other than 0, then the update is going to end up multiplying it by some factor here. Okay, but actually, like in order to derive this, like, right, like what's being written down here are just these errors for the two states, right? So here we have like W is the current approximation for the first state, and then the look ahead error is the reward, which is 0 plus gamma times 2W, right? But here we're saying, you know, there's some parameter value which is fixed, like W sub k. And that's what we're going to use here. And we want to figure out, you know, what should the current value of W be to minimize this error. And then this is for the second state. And again, we have the current, you know, whatever the estimated value of this state would be with W. And then in this case, there's two transitions, but this transition is just a value of 0, so we don't have to consider it. And this transition has, you know, this probability of 1 minus epsilon, and then gamma 2W because, or 2WK, because that is the value of the transition state. So then you can find the argmin of this by just differentiating this with respect to W. You know, that's what I'm showing here. So if you do the algebra and you set the derivative equal to 0, you end up with this solution for W, which matches what's in the book, right? And then again, like we have this multiplicative factor on W. So if gamma times this is greater than 1, then the conclusion is that these weights will just continue to grow indefinitely, and even though the correct values are actually 0. And, you know, it depends on epsilon. Now, you know, we know that gamma is always, you know, less than or equal to 1 in this problem. So if the threshold we get is greater than 1, then, you know, we don't actually have a problem, because then the problem's only going to be unstable if gamma is greater than 1, which it will never be greater than 1. And we can see here that, you know, if we take this quantity, this 5 over 6 minus 4 epsilon, right? We see like as long as gamma is greater than this, it doesn't diverge, which means 5 is greater than this. And we see that, you know, we could always have a condition, or sorry, that as long as epsilon is greater than 1/4, then this threshold for gamma is always greater than 1. And that's what's being shown here. So what's being shown here is for different values of epsilon, remember epsilon is this probability here. It's the probability of transitioning into the terminal state. So if epsilon is greater than 0.5, like if it's over here, then the gamma threshold where this is unstable is like, over 1, right? So all these cases, there is no divergence to worry about. But, if gamma is small, like less than 1/4, then we have all these different values of gamma for which this should, these weight updates will diverge. But in all of the, regardless of what gamma is, the values here should be 0, right? So it doesn't actually depend on gamma, but the stability of this does depend on gamma, which, is something of a problem because, well, I mean, we don't want divergent behavior to begin with. So yeah, but so if you notice, like, again, I have this comment here, but like going back to what I was saying before about the dynamic programming in the Baird example, like, can everyone see like what's wrong with doing this, or with saying that we want W to update in this way? I mean, here there's no policy to begin with, right? Like there's no actions here. This is just a Markov reward process. But they still wrote this down. So they wrote down this objective that we're minimizing and showed that it can cause divergent behavior. But again, there's a reason why this is causing a problem, and the reason is based on this objective. But can anyone, I mean, I had already said this in the previous example, but I'll give a second if anyone wants to, say or explain, why minimizing this would cause divergent behavior.
Actually, do you mind explaining it?
Yeah. No, I am going to explain it, but just wondering if anyone sees why that would be the case. I mean, it's nothing new. It's all based on stuff I've already said. Okay, so the problem here is that when we had defined like whatever we're doing here, it's based on this objective, right? Where we're taking, some estimate of this and trying to minimize the error. And we showed that with linear approximation, this converges, right? But again, it uses this, it only has meaning when we have this distribution here. And what's being shown here, again, we're going back to this case where we're just summing over the states, which is effectively just weighting all the states equally. And we didn't even consider what the distribution is here of the states. And it's definitely not equal in general. So fine, I mean, this is causing a problem, but let's actually try to, figure out what the on-policy distribution here is. Or in this case, there's no policy, but what is the correct distribution of visited states? So, to do that, it's not too hard for this problem where let's imagine, we start in state 1. I'm just going to call this state 1 and this state 2. We start in state 1, we never go back to it. So state 1 has 1 visit. And then the question is, what is the expected number of visits to state 2? Well, we can compute that expected value like this, where we take the sum over all the possible visits, and we take the sum of n times the probability of the number of visits being n. Now, you should be able to see here that, like, if we were to, like, the probability of visiting this state once is going to be the same as the probability that we just transition into the terminal state immediately, which is epsilon. Then if we stay here twice, it means that we did this once and then terminated after that. And the pattern continues so that whatever n is, we have this 1 minus epsilon probability happen n minus 1 times. And then the final transition here happens once. So we can write this down, convert it into this sum, and you end up getting a very simple answer, which is that the expected number of visits to this state is just 1 over epsilon. So, right, if epsilon is 1, then we just stay here 1 time. And then if as epsilon shrinks, then it just increases the likelihood of staying here longer. Okay, so does that make sense?
Yep.
So then if we want to figure out, what is mu, right? Mu is the probability, distribution for each state. So we have to take like the expected visit count and just divide it by the sum of the visit count. So here we have, 1 and 1 over epsilon. The sum is given by this expression, 1 plus epsilon over epsilon. And then to calculate the probability of each state, we have, for the first one, we just have the inverse of this because this is just 1. And then for the second state, we have 1 divided by epsilon times this inverse. So you end up getting these two expressions, right? And here I've plotted what that is as a function of epsilon. So if epsilon 0, we basically, we have no chance of being in state 1, and we spend all of our time in state 2 because we just stay here forever. And then as epsilon approaches 1, then the visit counts end up equaling each other, right? Because they each have an expected number of visits. It'll be exactly 1 in both cases. Okay? So as epsilon gets larger, it seems like, the true distribution is actually getting closer, right, to being equal to each other. And that means that this objective is now not that far off, right? Because here we're just imagining they have equal weight. So, that intuitively explains why as epsilon is larger, like in that case, if it's greater than 1/4, then these distributions are close enough that we get rid of the instability. But I'm going to show, so we can go back to the example, and now I'm going to write this expression down. So if you compare this expression to this expression, the only difference is that I've added this mu here, right? Everything else is the same. So this is like actually what you should minimize when you're doing these problems, because this is accounting for the state distribution. And then you can end up expanding this out. It ends up looking like this, except now we have these additional terms here for each mu. And then, if you go through the algebra here, I'm just, taking the derivative here in terms of w, setting it equal to 0. And then you end up getting this expression where, again, we have, whatever the existing parameter was times this constant. And, this constant, again, if it's greater than 1, this will diverge. So we have the gamma here. So we can come up with the condition under which, there's some value of gamma for which this whole thing will be greater than 1. However, we know that epsilon is between 0 and 1, right? So if you look at this expression, we have epsilon plus 4 and 2 minus epsilon. Now, here, this has to be greater than 4 because epsilon is positive, and this has to be less than 2. So this fraction is greater than 2. This is 1/2. So we have a condition on gamma, which is gamma is greater than something which is greater than 1, which will never happen, right? This is showing the condition on gamma for instability for different values of epsilon. And you could see the entire range of epsilon, this gamma threshold is above 1, right? So this will never diverge as long as we account for the state distribution, which is what we would expect because we had already, said that linear function approximation doesn't diverge. But here, like we can see again, like the source of the divergence here is that we're not using this state distribution in the update. And we can see that we do get convergence, like in these cases, like it doesn't mean the off-policy learning will definitely diverge. It just means that there are cases where it can diverge, and the cases appear to be cases where the two distributions are too different from each other, which is, for these small epsilon cases. You kind of see, so we know we never have a problem if epsilon is less than 0.25, and that is the case here. I'm sorry, there is always a gamma which causes a problem if epsilon is less than 0.25. We can see here that is to the left of this line where, right, these state visit probabilities are getting more and more different from each other. And there's some point at which they're so different that this gradient update no longer works. Or, at least it's no longer converging to anything, because this is not actually minimizing the value error. It's minimizing something that really has no relevance, because like the only situation in this problem where the states are equally visited is when epsilon is 0. Right. And even then, yeah, and if epsilon is 0, then I mean, sorry. The only time it's equal is when epsilon is 1, not 0. And clearly, when epsilon is 1, this value ends up being, 2/5 times gamma, and then, gamma has to exceed 1. So we're back to the case where it's not a problem anymore. So that, oh yeah, and then I have I had done this earlier, but there's some graphs showing I was like, if you initialize the weights at 0, then you never have a problem. But this is showing all this, I already showed it analytically, but this is showing practically. If you try to do this with on-policy learning, right? Like these are both the on-policy cases where it's perfectly stable, and then the off-policy case where the gamma is large enough that this diverges. And then it also diverges here. So are there any questions about this example? It's also, probably next time I used a similar example to this for a different concept later in the book, or later in this chapter. And I should make a note of what, oh yeah, what I mentioned, which is, what the, yeah, there was this point before that the TD fixed point is not always the same as the thing that minimizes the value error. And I'm not actually sure for this problem if that is also a factor. Yeah, but that's what you recall. This was from chapter, I don't know, it was actually from chapter 9. Right, we had shown, yeah, this random walk example. But right, in this example, right, this is kind of squashed, but we had shown that the solution, like the true Monte Carlo solution, doesn't actually match the TD zero solution. And that's because the TD fixed point for this is not the same as the true value. So that's another thing that can happen. And that has nothing to do with off policy learning. That's just what happens if you try to do bootstrapping. So here, because this is an episodic problem, you don't actually have to use bootstrapping to do this update, right? You could actually just sample the returns. And if you do sampling, that would end up, it should always converge to just W equals 0. Because if you collect samples, right, like the only samples you're gonna get from this problem are just 0 reward. So this whole thing where we use the next state, this only happens with the TD methods, right? It doesn't happen at all with Monte Carlo sampling. So we already know, like, it's guaranteed the Monte Carlo solution to this with the value error will just produce weights of 0. And then, yeah. So if in fact this is, I think from what I've seen here, if this problem doesn't diverge, then you have this type of update where this multiplicative factor is less than 1. And that just over time will just drive the W values to 0. And I think, that's what you see here. So here this is like doing, this should be showing whatever the TD fixed point is. So in this particular problem, the TD fixed point should match the best value error solution. But that's just because of how simple the problem is in the problem setup. That is not the case in general. I guess this exercise is just asking to go back to this counterexample here where we saw these weights diverge and show that the divergence happens with semi-gradient Q learning. Now, when I actually did this, and the way I'm doing Q learning here is like, I'm not following either of these policies. I'm just doing like typical Q learning where you just initialize a random policy and then the policy updates, try to find the optimal policy. Right, for this problem, there is no optimal policy. They're all optimal because like the only value you can get is 0 for any state. So you shouldn't get divergence because the values themselves diverge. But when I did this, and this is showing all the state action values found by Q learning, and all these values are 0. This is doing it with Sarsa, like semi-gradient Sarsa. And this is doing it with semi-gradient Q-learning. And I did not actually find that this diverged. So I'm not sure. I mean, if someone else wants to do this exercise, maybe they can see that. But I don't know why Q-learning would diverge in this case, especially if epsilon is small, because there was this comment here. Right, there's also a counterexample similar to this showing divergence for Q-learning. But it may be possible to guarantee convergence of Q-learning as long as the behavior policy is sufficiently close to the target policy, for example, when it's the epsilon greedy policy. And that is what I'm doing here, right? Like I'm using the epsilon greedy policy. That's also how you like typically perform Q-learning. So it may be the case that they're asking you to do Q-learning here where you just always use this behavior policy and you try to optimize off of that. That is certainly like a potential way to do Q-learning. But I think even if you do that though, like I did try doing that and the weights still didn't diverge. Like they might have diverged in the early part of training and then they still ended up converging to these 0 values. So yeah, I'm not sure under what case when Q-learning would break. I mean, I showed that this, yeah, like the semi-gradient method, it does diverge as long as you follow this behavior policy. So yeah, I guess Q-learning should diverge if you really only follow this behavior policy. But if you do anything differently, like try to actually do it normally, where you use the epsilon greedy policy, then like it seems to converge just fine. So, but maybe I could revisit this and yeah, see, like if you always yeah, but kind of similar to what I already said, it seems like if the behavior policy is sufficiently close to what you're trying to optimize, you shouldn't have this divergence, at least with this example. But yeah, but I'm kind of suspicious about this question because, I mean, like they say, counterexamples similar to this show divergence for Q-learning, which makes me think that this example doesn't diverge with Q-learning. Oh wait, sorry, Jay. Wait, are you saying that the divergence in this case relies on the states being like truly visited in equal number of times?
Yeah.
Exactly. Versus even just the noisiness of it, even if you're saying like even if you are following like this distribution somehow, but you're doing it through sampling, then you won't get this. Well, no, because this does diverge also. And this method is using this policy through sampling. But the problem is like if I make
But in this case,
epsilon,
epsilon greedy doesn't have a policy, so that means that it's going to keep on introducing alternative states. And
yes,
that's what creating.
Well, this instability is caused by visiting the states like evenly. But even if I make epsilon 1, that would be the
Yes.
random policy. But again, like the random policy won't do this because the random policy won't have this distribution. So, but it still seems like if you do Q-learning, like if you alter Q-learning so that like here where like I just have an explicit behavior policy, which is not epsilon greedy, but is like the behavior policy here, then it should diverge just like the TD method diverged, but I don't know. I wasn't seeing that either. And I don't know, like it's possible also that like as you do the Q-learning, like this is not the like there's no optimal policy, so the Q-learning doesn't even have to like
Yeah.
select something different from the behavior policy. So it may be that the way I'm doing it here, like the Q-learning really isn't doing off-policy learning because whatever the behavior policy is still optimal. Anyway,
Yeah.
so but I don't know. I could think about it a little more. But yeah, this didn't seem to fail. But it's sort of like it doesn't really matter because, you know, we already know that trying to do gradient learning in this manner is sort of a bad idea. Like you should always attempt to sample the states according to the correct distribution. Yeah. But anyway, I think, yeah, with these examples finished, the next part of the chapter goes into like more theory stuff, and I think we can probably continue that next time. And yeah, hopefully by then I'll have a better demo of this. They have this sort of diagram in the book about looking at the different objectives. And hopefully I was going to try to do this with like an actual concrete example to see how it all works in the different conditions. So hopefully we can look at that next time and then try to finish the rest of this chapter. Yeah, which isn't, but yeah, I mean, the chapter is like very conceptual. And it's all just about these pathological cases. But yeah, does that sound good to
Good.
everyone? Are there any remaining questions about, yeah, I guess really these two examples that we talked about?
No, thanks, Jason. I'm enjoying this. I'm glad I joined your session.
Yeah, great.
Because
Thanks for coming.
Yeah, these problems in
Thank
the
you,
real world
Jason.
means that you have to keep on. It's almost like you can't leave many of them to converge on their own. It's almost like you have to create structured interference to make them
These
work.
things.
Yeah.
Yeah. Are there? Well, yeah. We'll
Otherwise,
discuss. Yeah. And in the remaining part of the chapter, there's sort of, I mean, the goal hopefully of looking at all this is to understand the conditions where you wouldn't have this, you know,
Yeah.
pathological behavior. So that's always like
otherwise,
the goal of this.
because otherwise, practically, it doesn't end up working because you got like a stuck state that you can never get out of, and you need to have a condition or some kind of prior, or you need an additional alpha or some beta that you want to add to figure out how you're going to force it out of a stuck state. And that's probably later in the book. I haven't gone through the book. I'll definitely go through it. I like it. It's so far. Looks good.
Yeah, it's better. Yeah, I mean, part one is more like part one is the part of the book where you have really solid guarantees on a lot of what you're doing. And then, yeah, introducing this approximation in part two leads to a number of problems, which it doesn't mean you can't do it, but you have to be careful of a lot more things. Yeah, all the theory and math in part one is a lot more straightforward. But at least if you understand that piece, then you can understand, you know, what fails in the next case and maybe potential ways to avoid that.
And that's a
Hopefully.
fun part.
Yeah.
Definitely.
Okay. Well, yeah, thanks for coming, everyone. And yeah, we'll continue
Jason,
next time.